All right, I think we can get started with the next session. Hi, my name is UAI Choi. I'll be chairing this session. And so first up, please welcome our first speaker, Pascal Germain, to talk about bound to disagree generalization bounds via certifiable surrogates.
Thank you. Hi, everyone. So, first of all, I must give all the credit for this work to my PhD student, Mathieu Bézinet. Mathieu is in his final year of his PhD, and he did pretty much all the work for this paper. So we came with the initial idea. He even proposed the catchy title here. And he performed, of course, the proofs and the experiments. So I'm taking a few seconds to say that Mathieu will be on the job market soon, and he's actually looking for a postdoc. So if you are interested to talk with him, please feel free to send him an email. So I will start with some very basic notation. So we will work with a predictor or a model here, and this predictor or model is learned from a dataset S. We assume that the dataset contains RID sample from an unknown distribution. And here we will consider for the moment classification task. So the output space is classes from 1 to C. In this talk, we are interested in certifying a predictor H without relying on a test set. So for this, we will rely on generalization bounds that have this kind of form. So here, given a loss function L, the bound will have this kind of shape. So the bound says that the true loss on the distribution D is bounded by the empirical loss on the training sample plus a certain complexity term. But in this talk, we really want to develop bound that we can use as numerical certificate to certify our predictor. So for this, the complexity term must be, of course, as small as possible because we want the bound to be tight. And of course, it needs to be computable. We don't want the complexity term to include unknown quantities. The good news is that there are already a lot of such bounds out there. Here we will divide the bounds in three family of classical frameworks: the model compression framework, the sample compression framework, and the pack-based framework. So for the model compression framework, the complexity term, epsilon, rely on the description length of a compressed model. For the sample compression framework, the complexity term, epsilon, relies on the size of what we call a compression set, which is a subset of the training sample from which we can reconstruct the predictor. So pretty much as we've seen in the keynote talk this morning. And finally, the pack-based framework is interested by certifying the expected risk over a family of predictor given a posterior distribution Q, and the complexity term here will be the divergence, the KL divergence typically between the prior, a prior and the posterior. I really think that people should use more this kind of framework to obtain certificate on nowadays models, but it turns out that unfortunately they are not used so much in practice. And one reason is because they rarely give tight bounds for deep or large models that are learned with the everyday recipe. Instead, if we want to obtain tight bounds with this framework, we need to apply special recipes that allow to learn a model that performs well as a good accuracy, but also control the complexity term. But what if one wants to certify a model that is already trained? It's the question that we answer here by our main result that relies on simple key ideas, but ideas that are fruitful. So what we propose to do is to train a certifiable surrogate that we will call H here, that is close to the target model. And so we are able to obtain a tight bound on this surrogate model. And after that, we will compute a bound on the disagreement set. So it will be bound the disagreement between our surrogate model and the target model that we want to bound. So here, we still need a set that of sample that the model doesn't know about when we train the model, but this set is unlabeled, so it's much more easier to obtain. So the results that I will present will rely on this simple kind of bound. So we want to bound the target loss of our target predictor F, and we will upper bound it with high probability by the bound on the surrogate model plus the disagreement bound. In the paper, we explore various kinds of disagreement. Here, due to time constraint, I will only present two. The first one is applicable when we want to bound the 0-1 loss of the target model. So when we want to bound the 0-1 loss, the disagreement that we need to compute on the unlabeled set is only the probability that the target and the surrogate doesn't output the same answer. So here I recall you that we are in a simple classification setting. And we can compute this on the unlabeled set U. And after that, we can obtain a generalization bound on this quantity. And here we apply a tight bound, which is given by the binomial inversion, which is greatly inspired by, for those who know, by by John Langford, who wrote a GMLR paper on statistical learning theory back in 2005. If we want to bound another kind of loss, we will need to make some assumption on the loss that we want to bound. Here, I present a result for losses that are Lipschitz, and what we will compute as disagreement here is the L1 distance between the softmax output of two models. So we base this result on the fact that nowadays the softmax is often used as the output layer of a neural network. And this time, inspired by a result by Fang and al., we can use a Chernoff inequality to obtain a bound that relies on the inverse of the binary KL divergence. So those two bounds are computable on the unlabeled sets. So in the paper, we also present some other results, including an extension to a disagreement measure, but that disagreement that is computed between the target model and the expectation according to a distribution over surrogate, which is really reminiscent of pack-based bounds for those of you who know pack-based. We also present in the paper a weaker result that allow to bound non-Lipschitz losses, but it's weaker because now we removed the fact that we rely on an unlabeled set, and we need a new set of label to compute this disagreement on non-Lipschitz losses. So for the remaining of the talk, I will present how we can use these bounds to obtain tight bound on the target models, and I will present 3 use cases. The first one will be to certify a target model using an independently learned surrogate model. The second one is similar, but we want to go further. We want to learn a surrogate model that minimizes the disagreement with the target model, and we will use distillation technique to achieve that. And the third use case is when one wants to replace a legacy model by a preferred one and bound the performance gap between these 2 models. For the first use case, so it's the more simplest one. Here we have a target model F that is complex, and we want to obtain a bound on its loss. So we train a certifiable surrogate that I call H star here, and to obtain the bound on the target model, we will compute the bound on the surrogate and compute the disagreement bound between the target and the surrogate. So here I present you some result that is obtained for the 0-1 loss on bonding the generalization loss of standard CNN network on the MNIST dataset and ResNet 18 on C14 dataset. Here, the surrogates are not, in fact, simpler models per se, but they are the same architecture, but they are trained to optimize the bounds. So we optimize different kind of bounds. We can see results for bounds that stem from the simple compression framework, Bayesian framework, and model compression framework. And the 2 first results that I compare to is bounds that we obtain by trying to bound directly the target model with some bounds that were available and computable, so norm-based bound and partition bounds. So we can see that with our method, we obtain certificates that are magnitude tighter. For the second use case, we want to learn a surrogate that minimizes the disagreement with the target. Here, the caveat is that in order to do that, we need to write a bound that is valid for all possible surrogate. So we consider a posterior distribution Q over the surrogates, a prior distribution, sorry. We need to specify the distribution Q before computing the surrogates. And the caveat is that often we obtain loser bounds because of this. But still, here I present bounds that we obtain on quite large models, so this Dilbert and GPT-2. So here it's bound on the Huber loss, that is a loss that is Lipschitz. The target models are this Dilbert and GPT-2 that we fine-tune on Amazon polarity dataset. So the test error and the bound here are losses on the Amazon polarity dataset. And the surrogates are obtained also by fine-tuning this Dilbert and GPT-2 on these datasets, but with a very compressed sub-LoRa adapter. So the obtained model is very compressed. You can see the size here is very tiny. And this is trained by distillation. So what we did basically is to obtain a pseudo-label on the unlabeled dataset using the target model and use this pseudo-target to learn the surrogate. Finally, the third use case is an alternate way to use the disagreement bound. So here we will not bound directly the surrogate, but imagine instead that we have an in-production model that people really like out there, and we want to replace this model by another one that has some qualities, say it has less memory footprint, or the inference time is faster. So here we can use the disagreement bound to bound the performance gap between the 2 models. And what I present here is some bound that we obtain on the performance gap between two networks. It's again bounds on the Uber loss. The legacy models here that we want to replace are the same that were presented in the last use case. But here for the candidate model that we might use to replace the legacy model, we explore some quantized variance obtained with library out there to train continuous network. And we can see that, in fact, we can choose, we can use this bound on the performance gap to guide which model would be the model we choose for replacing the legacy models. In summary, we presented new disagreement bounds that we can use to certify complex models via simpler certifiable surrogates. I presented you 3 use cases, but we can think of more. And notably, we obtain quite tight bounds, so what we call non-vacuous bounds on large NLP models, such as Distilbert and GPT-2. Thank you.
All right, we have time for some questions? Yeah.
Okay, this is going to be a bit of an open question. So many decades ago, the work by Babnev and Chervonenkis, the VC dimensions, in some way it aided in the design of support vector machines and a lot of the theory that came from it. And so I wanted to take this opportunity to ask you, given the great extent of your contributions to PAC-based, how optimistic are you that at some point the PAC-based theory, which I guess in some way is like the heir of VC dimension bounds and those kinds of techniques, will aid in the design of training algorithms or maybe model architectures for deep learning?
Yeah, it's an open question. I don't have an absolute answer to this, but I'm spending so much effort in developing the PAC-based theory because I think it can already be used, in fact, to certify models. So I would really like that people developing PyTorch or other libraries include some PAC-Bayesian objective in their standard library for people to be able to minimize this kind of bounds, because it actually gives quite tight bounds, and often the models are performing quite well. So the question, according to me, is more, do people will adopt it, would realize that it's very it can be very useful to certify models with this kind of bounds. So.
Thank you very much.
Questions? I could ask one. So what kind of surrogates did you use, and could you say a little bit about like the size of your surrogate versus the target models and how that affects?
It really depends on the experiments that I present. And in fact, here I choose some experiment to show you, but in the paper and the appendix, Matthew, my PhD student that did all this work, tried a lot of kind of models and configuration. But for what I presented here, what I can say for the second use case, sorry, here the bounds are obtained on fine-tuned models. So here, for example, we use the exact same models, but for the surrogate, we freeze a lot of the hidden layers, and we train like it's written, a sublabor adapter, which are really tiny matrices, and it's for that we can obtain quite tight bonds. So I don't know to which extent it answered the question, but and also maybe another thing that I can say is that if for the use case 1, we obtain very tight bound with the sample compression, framework. So here, like I said, the models are the same, but in fact it's the way the models are trained that are different. And the sample compression framework allows to train the network from a really tiny set of samples. And in fact, the bound that we obtain in this case it's like a test set bound, but on the complement of the compression set. So the example that we're not used to train the surrogate.
All right, and let's thank the speaker again. All right, next we have Daniele Nikza to talk about scaling up Bayesian DAG sampling.
So, hi, thank you for coming. And now we'll describe our new paper that is scaling up Bayesian DAG sampling. So we are within the Bayesian networks framework. Specifically, we advance MCMC methods for sampling DAGs that are directed acyclic graphs. And this is basically the structure of the presentation. I will first introduce a little bit the framework, and then I will describe our two main contributions. We basically speed up two existing algorithms, and we combine them together to scale up DAG posterior inference to large networks where the current state-of-the-art fails. So the object in Bayesian networks are directed acyclic graphs where edges encode the conditional dependencies between variables. And for example, here there is an edge that goes from node 1 to node 2. So basically, we say that node 1 is a parent of node 2. And we want to infer the DAG posterior that basically tells us how likely each possible DAG is the data generating model. And of course, since the absence of edges encode the conditional independence between variables, we can decompose the joint probability distribution as a product of univariate probability distributions, where basically each node depends only on its parents. But there is a problem, as the number of DAGs grows super exponentially with the number of nodes. Therefore, we cannot analytically compute the posterior probability of each possible DAG. Therefore, we have to rely on approximate methods for large networks as they focus on modeling the high probability regions of the posterior distribution. So we are within the structural MCMC framework, where we basically construct Markov chains by sampling DAGs. And here, DAGs are proposed by local changes to the structure of the current DAG in the Markov chain. So we may add, remove edges, or we may resample entire parent sets. And we want to estimate low-dimensional marginals, for example, the edge posteriors. And these are really easy to compute, because basically we have just to count the number of DAGs in the Markov chain that contain that specific edge, and we have to divide this value by the total number of DAGs that have been sampled by the Markov chain. And here we rely only on unnormalized probabilities that we call scores to propose and accept DAGs. And here, for example, the score of a DAG is the product of unnormalized node probabilities that we call node scores. And these node scores are really easy to compute, so we perform a preprocessing phase where we compute and store the node scores for all possible parent sets. Let's go to the first contribution. We basically accelerate the single edge moves by Giudice and Castello. And before going to our implementation of these single edge moves, I want to describe a little bit this original version. So we first propose a graph Gij by randomly adding, removing, or reversing an edge in G that is the current graph in the Markov chain. And then we perform a rejection sampling step. So we basically check if Gij is acyclic. If it contains a cycle, we just reject it. Otherwise, we compute an acceptance probability because this algorithm has been designed within the Metropolis Hastings framework. But how can we propose these single edge moves? We need to first sample a node pair uniformly at random. For example, if the node pair is 1, 3, since there are no edges between the nodes 1 and 3, we propose the DAG by the graph by adding that edge. The second move type is the edge removal. So for example, here we sampled the node pair 1, 2, and since there is an edge that goes in the same direction as the one suggested by the node pair, we propose the graph by removing that edge. And the last move time is the edge reversal. So for example, here we sample the node pair 3, 2, and since there is an edge that goes in the opposite direction as the one suggested by the node pair, we propose the graph by reversing that edge. And let's now continue with an example. So basically, this is the graph that we have proposed. And as I said before, we perform an acyclicity check where we basically reject cyclic graphs. But here, there are no cycles. So we proceed to compute the acceptance probability. And here, now we understand where the problem might be, as we spend a lot of computational resources to propose a graph, to perform an acyclicity check, and then we compute an acceptance probability, and still the acyclic proposal can be rejected. So the idea behind our implementation is that we want to propose DAGs only when they get accepted. And of course, to do so, we set the proposal distribution of GIBB, which is our algorithm, equal to the transition probability distribution of the Giudici and Castello algorithm. So we sample a graph Gij with a probability that is equal to Qij, which is the probability of sampling the node pair ij in the Giudici and Castello algorithm, the one that we saw before, multiplied by the Giudici and Castello acceptance ratio. And if we do so, we basically propose DAGs, and they always get accepted. But there is a problem here, since for each neighbor Gij of G that basically can be obtained by adding, removing, or reversing an edge in G, we have to compute this transition probability. And here in the nominator, of course, we have to compute the score of this neighbor. And this involves performing an acyclicity check, as we have to assign 0 probability to cyclic graphs. And of course, if the graph does not contain cycles, then it becomes the product of node scores. But we don't want to compute so many acyclicity check per move. So we do something that is slightly different. When we compute this transition probability, in reality, we do not perform an acyclicity check on Gij. Indeed, now we call it score star of Gij. And cyclic graphs may have positive score here because we don't know if they contain cycles. So the algorithm is the same, basically, but there is a rejection sampling step. So now we first propose Gij with probability P star, and then if it is acyclic, we automatically accept it, or otherwise we reject it. So the advantage here is that we perform only one acyclicity check per move, rather than one for each neighbor. But how can we implement this efficiently? So for each node pair ij, we store the move associated with the node pair, and bij, that is basically the transition probability P star that doesn't take into account the cyclicity checks. For example, here for the node pair 1, 2, the associated move is remove the edge that goes from 1 to 2, and we store B1, 2, that is this P star. And we do so for each possible neighbor. Then we compute B, that is the sum over ij of bij. And since bij is the transition probability of a neighbor, then B is the transition probability to any possible graph, to any neighbor. And more importantly, 1 minus B is the self-transition probability of the algorithm. Therefore, we can simulate K self-transition by just drawing from a geometric distribution. Then after self-transition in K times, we sample a move with a probability Bij divided by B. For example, here, we sample the move, remove the edge that goes from 2 to 3. And since there are no cycles generated, we accept automatically the new DAG, and we update the data structure. But since the score of a DAG is the product of node scores, we have to update only a few entries of this data structure, and it's really fast. And of course, like if the proposed graph contained a cycle, we had to reject it. So let's now compare the performance of these moves. So we compare our algorithm to the Choi and Castello version on different datasets sampled from benchmark networks of different sizes. And the smallest network has 37 nodes, while the largest one has 441 nodes. And here I want to show the average value of B, because basically, for each move, we can simulate thousands of self-transitions, because the value of B is really small. And that's why basically GIB it's up to 200 times faster than the Choi and Castello algorithm in this datasets. So let's go to the second contribution. Here we accelerate the parent set resampling moves. This is a class of move that is quite broad, but I tried to simplify those moves as much as I could so we can focus on the core mechanism that they share. So how do they work? We first select a node I. Then we orphan it by removing the incoming edges. And then we find the candidate parents of I that are basically its non-descendants. And the idea behind this is simple, because if the new parent set of I contains its descendants, then it means that we would generate cycles. And of course, we don't want that. Then we have to find the possible parent sets. And different moves can set different constraints on the new parent set. Some moves, for example, do not set any constraint. Therefore, like the new parent set can be any subset of C. And these are the possible parent sets in this case. Otherwise, some moves may force one node J to be a parent of node I. Therefore, the new parent set can be any subset of C that contains J. And in both cases, then we have to sample a new parent set from the possible parent sets with a probability that is proportional to its score. And we see where the problem is now. As in the denominator, there is a normalizing constant that basically is the sum of the scores of all possible parent sets. And for large networks, the set of possible parent sets is huge. Therefore, we developed a score pruning technique that discards in the pre-processing phase the low-scoring parent sets, so that basically this normalizing constant becomes the sums of much fewer elements. And we have an approximation guarantee for this scoring pruning technique as the total variation distance and the KL divergence between the true posterior distribution of DAGs and the pruned posterior distribution are bounded by a value that is equal to epsilon that we can basically arbitrarily choose. I will skip the details due to time limitations, and I will just go to the results. Here, basically, we report the percentage of parent sets that are kept after score pruning. And this value is quite important because it basically tells us how much we can speed up these parent set resampling moves. For example, if after score pruning only 0.1% of parent sets are kept, then basically it means that we can speed up these moves by roughly a factor of 1,000. And this is basically the last slides. Here I want to show the performance of GIB, that is our sampler, that now basically combines both classes of moves. And here I show the trace plots of the five independent MCMC runs on large networks, where on the x-axis we have the sampling time, while on the y-axis we have the score of the DAGs. And here we can see that the 5 runs manage to mix well and basically approximate well the DAG posterior, where the current state-of-the-art fails. And that's all, so thank you for listening.
We have time for some questions.
Thank you for your talk. a little more than 20 years ago, Nia Friedman and Daphne Koller had proposed an approach to learn DAG graph structure in which they were addressing the difficulty of checking acyclicity by conditioning on the topological order of the graph. And this had the advantage that it was possible essentially to resample, like to include or change nodes or parent sets in parallel, and also like without having to check acyclicity. So this is a paper that's called Being Bayesian about the network structure. So I'm wondering if you consider that, and if you have a way of comparing maybe this type of approach to the approach that you're presenting.
So basically, for example, this BiDAG method, I don't know if it addresses the question. This is an MCMC sampler on node partitions. So basically, we compared also like our sampler to different methods, also to a generative flow network method, and yeah, we tried to compare our sampler to also like different MCMC methods that, for example, use sample in the space of node partition, like this one. So, and of course, like for the acyclicity checks, like this can extend a little bit the answer. We perform both search algorithm for acyclicity check, but also we use the data structure to keep track of the acyclicity check. And in reality, like we tried different approaches, and they didn't really change that much the performance of the sampler. That's why I didn't even like include this in the presentation. But if you have further questions, maybe we can even discuss in the poster session.
You said at the start that you start off by computing all the scores for all possible parent sets.
Yeah, exactly.
But for...
Sorry, I don't see you. Where are you?
Yeah, I'm here.
Okay.
But for 200 nodes, isn't that already infeasible?
Yeah, it's basic. Of course, we have a maximum in degree, but then also like the advantages of this score pruning technique here is that we have also an heuristic that basically provides us with a stopping rule for the pre-processing phase. So basically, we compute the node scores in increasing size, and then basically we know at some point that all the remaining scores are negligible. So we stop the pre-processing phase, and that's another big advantage of score pruning. And unfortunately, I didn't put everything, like I couldn't put everything in the presentation, but that's another big advantage of score pruning.
Thanks.
Are there any other questions? Right. If not, let's thank the speaker again.
Thank you.
All right. Next, please welcome Xia Wu to talk about learning representations from perturbation, a novel matrix view weighting framework for naive Bayes.
Good morning, everyone. It's a great honor to present our work at the UAI conference. The title of the paper is Learning Representations from Perturbation, a novel metric view weighting framework for naive Bayes. At a high level, this work aims to improve naive Bayes classification from a representation learning perspective. Wu Xia from Zhejiang University, the first author of this paper. Let us start with the background. Naive Bayes is one of the top 10 algorithms in the mining. It naively assumes that all attributes are independent, which is rarely held true in the real-world applications. So many enhancements have been proposed, which can be generally divided into 5 categories: structure extension, attribute selection, attribute weighting, and instance selection and instance weighting. Among them, attribute weighting is an important category because of its flexibility and strong performance. And However, existing attribute weighting methods mainly focus on designing novel weighting strategies, which rarely host, and most of them mainly rely on focus on the raw attribute, which is insufficient to capture the complex data characteristics in the complex real-world applications. So, to address the issue, a multi-wheel weighting framework has been proposed, which constructs multi-wheels beyond the raw attribute, and then it learned the weighting naive Bayes within each wheel. And there are several representative methods. The first, attribute augmented and weighting naive Bayes term Z squared WNB, it constructs random one-dependence estimators to augment the raw attribute by concatenating the raw attribute with the predicted higher labels of all these. And further, multi-wheel attribute weighting naive Bayes, it constructs super-parent one-dependence estimators and random trees, and use their predicted class labels to generate 2 additional label values, and then need to train the 3 weighting naive Bayes models. And further, enhanced multi-wheel weighting naive Bayes use cross-correlation strategy to reduce overfitting risks in the wheel construction model, and then learn wheel-specific weight for each wheel. Finally, dual-wheel weight naive Bayes use k-ins to construct another additional wheel, and then it learn a specific weight for each instance. And however, this existing multi-wheel framework still have 2 limitations. The first is all the basic spheres used for wheel construction are trained on a fixed input distribution, and the second idea is that the lantern wheels disregard the posterior probability and different probability differences between different basic spheres. So to address these 2 issues, we propose our perturbation driven metric wheel weighted framework, termed as PMMB. The first idea is to apply diverse input progression, and the second idea is to jointly utilize the hard labels and the soft probabilities of basic spheres. And the model of this framework consists of 3 models. The first, base wheel construction and lantern wheel construction, and finally, multi-wheel weighting and fusion. For base wheel construction model, the goal of this model is to implement input perturbation, and to the end we get the first and the second base wheels, and by applying unsupervised and supervised perturbation. And for unsupervised perturbation, we use equal-wise discretization, and for supervised perturbation, we use the minimum discretization lines principle. And by applying the 2 different perturbations, we may map the same raw attribute value into a different discrete indices, so we get different base wheels, and which will provide a different input perturbation for the input foundation for the following latent wheel representation learning. And the second model is latent wheel construction. And this consists 2 phases. First, for base classifier training, we train 2 types of base classifier examples. And for superparent and one-dependent estimators, each raw attribute in the corresponding will survive the superparent in turn. And for random trees, the data is supplied with information gain by randomly selecting a subset of attributes. And for lantern representation learning, PMMB extracts both the hard labels and the soft probabilities, and concatenating them as the high-level representation. And so after organizing this base wheel and lantern wheels construction into a metric wheel, we further address the attribute redundancy within each wheel and learn the class subseq value ways, and we use the objective function is the negative likelihood without regulations, and the test instance will be first mapped into the base wheel and lantern wheel construction by using the same wheel construction process. And finally, our method average all the results and finally predict the class with the highest probability. And next, I will show the experiment and the results. We compare our method with 7 most related competitors, and on 59 benchmark their size from UCI repository. And as shown, the data size covers a wide range of class counts attribute invariance and instance scales. All the experiments are employment on Weka. This slide shows the overall classification performance, and the number between each method is shows average rank with lower is better, and in each cell, each cell will repose the geometric mean occurrence rate, the wins, draws, losses by comparing the classification occurrence, and the second to repose the p-value of the Bayesian test. We repose our Bayesian test p-values. And the result shows that it achieved the lowest average rank is the highest geometric mean occurrence, and statistically outperforms other competitors, and in particular it outperforms the most two closest multivariate frameworks, EMWB and MEWB, which means that our perturbation-driven metric view constructions effectiveness. And then to examine these different effectiveness or different components, we implement ablation study. We comparing our method with the string variance without generating length values, without the MDLP branch, and without the AWD branch. And the result shows we have two key findings that with moving generated length values, removing without either MDLP branch or either AWD branch, we found that relying solely on fixed input distribution greatly limits the diversity of our generated attribute. And removing the generated length values, we also discredit the performance, which shows that the higher level, the utilization of higher labels and soft PPTs can explore higher level attribute. Further to examine rigorously validate our effectiveness in exploring diverse data representations, we conduct an error ambiguity deposition, and by applying this equation, the final example error will be decomposed into two parts: the average individual error and the example diversity. And in the scatter plot on the left shows that compares PMWB with MAWB across a 59 data size, and the right point shows PMWB outperforms MAWB, and the horizontal axis shows differences in ambiguity, and the vertical axis means difference in ambiguity in individual error. And this side on the right side means we get our method achieves higher ambiguity on more than 80% data size. And the right figure shows the representative data size, which means different in every example trade-off partner. And for each group, the solid bar means the individual, solid bar means the final example error, and the scatter bar means the example ambiguity, and their summation of the means correspond to the average individual error. And for artificial characters, it improves both the average individual currency and the ambiguity. And for Australians, it gets similar individual error, but the gains mainly comes from a higher ambiguity. And for those, it sacrifices the individual error, but the larger ambiguity comes for the losses, so it gets the final lower example error. And further to validate its flexibility and flexibility of our framework, we construct another IXT extension variant by adding a new perturbation called proportional K-interval discretization. As shown, it achieves lower average rank, but no statistically significant or improvement. And what more, it introduced more computational costs. So considering both the performance and the computation costs, we choose MDLP and AWD branch as the default configuration. To conclude, we extend our conventional metric wheel representation into metric wheel framework. And the second is we propose a novel wheel construction model. And finally, we conduct extensive experiments and provide some in-depth discussions about our method. And for future work, we will investigating more perturbation strategies for the mixed type data. Thank you very much for attention.
All right, we have time for some questions. I don't know if this is spoilers, but could you say a little about the mixed type data?
Yes. Could you please repeat it again?
I guess what the bottleneck or the challenge there is to apply this for mixed type data.
Because our discretization method is mainly focused on the numeric data side, and all our 59 data size is most of them numeric data. So the future work we will apply some, for example, masks file method to apply or input different input directions on the mixed type data and some categorical and with numeric data.
Is there any other question? Could ask one more actually. This might be more of a general question about the kind of multi-view with like naive-based classifiers. But do you think a similar kind of approach could help for other type of Bayesian network classifiers? So is in like where you also have kind of independence, conditional independence assumptions. Can some of these ideas like generalize there as well?
Sorry, could you repeat again?
So I guess one way to maybe rephrase this is these ideas, can they generalize like beyond naive-based classifiers and other type of like Bayesian networks?
We compared the main experiments. We compared the main experiments. We compared with seven most related classifiers, and these, for example, the random we compare it with our basic classifiers we used in the framework, the superparent multiple estimators, and the random forest, and the result shows it it outperforms the basic classifiers.
Thank you. Thank you. All right. In that case, let's thank all the speakers again, also the volunteers.